Hello, this is finding significant features for fusion learning using dimensionality reduction techniques. Fusion learning is a fairly new method that specializes in problems where we have little amount of data. The goal of this method is to classify categories that hasn't been seen before with just a handful of samples. In this example, we have the support data of 3 classes with only 2 instances for each one, and we want to classify the query image by only seeing the support data. Metric learning methods has demonstrated that simple models can achieve good performance by learning a similarity function to compare the support and the query data. In this example, we show the prototypical networks, a metric learning method which calculates the prototypes from each class based on the feature embeddings and compare the query with each prototype using the Euclidean distance. We believe that this method may not exploit the information given by a specific fusion task. So in this work, we explore the use of dimension reduction techniques as a way to find task significant features. The proposed model follows the metric learning setting, adding a layer between the feature extraction and the metric learning similarity comparison. Given the feature embeddings, we apply several dimension reduction strategies and obtain an intraclass and interclass score for each one. These scores are used to select the method which help us to obtain the best dimensions for the current tasks. These new features obtained are then used by a metric learner to produce a classification. In this case, we use UMAP, ISOMAP, and PCA to reduce dimensions. The ICN Score is a normalized measure that combines the distance and variances of the inter and intra-k nearest neighbors of each instance in the data. The formula is made up of 3 main functions. Lambda penalizes the neighbors of xi with the same class based on how distant they are, and punishes neighbors of different classes based on their proximity. Omega penalizes the distance variance of the neighbors. High variance is not desired because it increases the probability of overlapping among classes. Gamma describes the ratio of neighbors classes, where all the neighbors being in the same class of xi is preferred. We also have control constants to give different importance to the functions. This is a visual example of how we would write the features given by the fusion task. A task with distant clusters between classes and with low variance among the class will be given a better score. Up until now, we obtained an improvement of around 1.5% for the 5-way one-shot setting on the test set using prototypical networks. We also achieved a better performance than matching nets and relation nets on 5-way 5-shot setting, but obtained around 0.5% less accuracy than prototypical nets. There are still some design choices we need to test in order to decide whether our technique can help the accuracy of the baseline models.